Good morning, students. In last class, we discussed about the rectifiers. In that, we discussed the off-wave rectifier, Sanitapur full-wave rectifier, and bridge rectifier. So, in these three rectifiers, we are getting always output as pulsating DC. So, in our power supply circuit, which converts from pure AC to stable DC output. So initially we are converting from pure AC to pulsating DC. So that means the pulsating DC contains the AC components as well as DC components. So to eliminate the AC components in the pulsating DC, we are using the filters. These filters are used to eliminate the unwanted frequency components. So here we'll discuss about the filters. So this filter is a frequency selective network which passes desired frequency and eliminate unwanted frequencies. So these filters are one of the major blocks in the power supply system. So we know in our rectifier outputs harmonic frequencies that are omega naught, 2 omega naught, 4 omega naught, 6 omega naught in of a rectifier, and 2 omega naught, 4 omega naught, 6 omega naught, 8 omega naught in the full wave rectifier. These are the harmonics present in the our rectifier outputs. These harmonics we need to remove by using the filter circuits. So in filter circuits mostly we will use capacitor and inductor elements. By using these large capacitor and large inductor values, we can eliminate these harmonic frequencies. Yes, this large capacitance offers the low reactance and large inductor offers the high reactance to the AC components. By connecting the capacitor and inductor elements in the filters, that means by using this capacitor and inductor as a filters, we can eliminate the unwanted AC components from the output of rectifier circuits. Yes, so now we will discuss about the capacitor filter. So either we can use capacitor as a filter or inductor as a filter, or both the combination. Capacitor and inductor combination is also used as a filter. So initially we will discuss about the capacitor filter. We know this capacitor filter is used to eliminate or reduce the AC components, and this capacitor is connected in parallel to the load resistor. Now you can observe the block diagram of capacitor filter circuit used in the rectifier. So what are the output received from the rectifier? It is pulsating DC. In the pulsating DC, we are having AC components plus DC components. To eliminate or to reduce the AC components by using the capacitor, we are connecting the that capacitor to parallel to the load resistor. Clear? For proper filtering, capacitor should be selected such as that reactance of capacitor is less than load resistor. Clear? So we need to consider the reactance of capacitor must be very small compared to the load resistor. So we can write the reactance of the capacitor can be written as 1 by omega into C. Yes. So here we are writing the 1 by omega into C is less than RL in of a rectifier, and coming to the full wave rectifier we are writing it is 2 omega naught, 1 by 2 omega naught into C. Then we are writing 2 omega naught. Why? Because here we are having the output frequency is 2 F naught. So in of a rectifier we are having F naught, output frequency is F naught. So that's why we are writing it is 1 by omega naught C is less than RL in of a rectifier. 1 by 2 omega naught C is less than RL in full wave rectifier. So to use this capacitor as a filter, we must consider the reactance of capacitor must be small compared to the load resistor. Yes, so you can observe the capacitor and load resistor forms the voltage divider. Yes, so these two form the voltage divider. Sorry, this capacitor and load resistor forms the current divider. Yes. So these two are connected in the parallel. So the two elements form a current divided circuit. So we know output of rectifier is pulsating DC. It's a combination of AC plus DC. So whatever the current coming from the or coming from the rectifier, that is divided into capacitor as well as load resistor. That AC components flows almost through the capacitor. Why? Because when we are applying the AC components, that means the frequency of AC component is not equals to 0. So when frequency is not equals to 0, what happens? The reactance is very, frequency is not equals to 0, the reactance is 0. Yes. So the frequency of AC component is more, that means omega term is more, so reactance is less. Yes, due to the low reactance of the capacitors, so that AC current flows through the capacitor, and DC, it does not allow the DC current. Why? Because when you are applying the DC, so the capacitor will open circuited. So the DC will moving through the load resistor RL. So whatever the current coming from the rectifier, so the current is, or AC current is flowing through the, or entering into the this capacitor, and DC is entering into the load resistor. So we are separating the AC and DC by using the capacitor and load resistor. Clear? So the most of the AC components or AC current is flowing through the capacitor, and small amount of current, AC current is flowing through the load resistor. Yes, and most of the DC current is flowing through the load resistor only. Yes, because our capacitor will not allow the DC components. Clear? So now we are dividing the AC components and DC components. Clear? So when you are applying the, when you are connecting the this capacitor and load resistor in parallel, that DC is moving into the RL and AC is moving into the capacitor. So what we are taking the output across the load resistor. So when you are considering the DC output, that means during the time, that output during the time period, during the DC current flowing through the RL, we can get it is equals V naught equals to IDC into RL. Clear? So here we are separating the AC component from the pulsating DC. Clear? So now I am considering the, so my capacitor filter is connected to the off-air rectifier output. Yes, my off-air rectifier is output. My off-air rectifier output is connected to the capacitor filter, and we are taking the output across the load resistor. Clear? So when diode is in forward bias, what happens? When diode is in forward bias, the diode is short circuited. If I am assuming my diode is ideal, then what happens? So my, in the time period, my capacitor is charges. Yes. So my capacitor charges through the diode where it is a forward bias. So if I am assuming ideal diode, that means there is no drop. So whatever we applied the input voltage, it is Vm sin omega or Vm. So up to that peak inverse voltage, my capacitor will charge. Yes. Yes. When the diode is in reverse bias, what happens? So there is no current passing from the diode. So now my capacitor is discharging. Now my capacitor is discharging through the load resistor. Yes, when diode is in forward bias, my capacitor is Vc. The voltage across the capacitor is Vc, charges up to Vm or Vi. Why? Because if I am assuming ideal diode. So when my diode is in reverse bias, my capacitor is discharging through the load resistor. Yes, since the discharging time constant is RL into C, it is very large. Why? Because if I am considering a very small time constant RL into C, what happens? My capacitor discharging immediately up to 0. Yes, so as a engineer, I am not allowing the discharge. I am not allowing the discharging immediately. So I am increasing the time constant. That means discharging time constant very large. So that RL into C is the discharging time constant. It must be high value. Yes. If I am considering very small value, my capacitor will discharge immediately up to 0 volts. Yes. To avoid the speed discharge, we are increasing the time constant RL into C. Yes. So due to that large time constant, the capacitor discharges very slowly. So here you can observe the waveform. It is my input sinusoidal signal, and initially it is T naught. Then the maximum peak voltage it is Vm at T1. Again T2 it is somewhere voltage, and T3 is also peak voltage. So during the time period of T naught to T1, what happens? So during the time period, it is positive off cycle. In this positive off cycle during the T0 to T1, my diode D1, my diode D is in forward bias, so it is in conduction. Yes. So diode D is conducts. My capacitor charges through the diode D up to peak input voltage. Whatever the maximum voltage, it is Vm. Yes. In this case, I am assuming my diode is ideal one. Yes. If it is not ideal, then by reducing the Vm minus some drop across the diode. Yes. So after charging up to Vm, what happens? Now I'm considering the second case. It is T1 to T2. Now my capacitor discharges slowly. Yes. So in this case, now this in this case, my capacitor discharges slowly through the RL resistor. Yes. So how much it is discharging up to VR, triple voltage. Yes, my voltage VC is decreased by an amount of ripple voltage VR. Why? Because it is discharging slowly because of my time constant. I am setting that RL into C is very large value. So due to that, discharging time is high and charging time is very small. Again, next case, if I am cancelling T2 to T3, again my diode is in conduction. Again, the capacitor is charging from this Vm minus Vr. Yes, it is charging up to Vm minus Vr. Now it moves, or it is charging from Vm minus Vr to again maximum value Vm. Again, next case it is moving from Vm to Vm minus Vr. Again it is charging from Vm minus Vr to Vm. Again it is moving from Vm to Vm minus Vr. So it is continuous process. It is charging and discharging. It is charging up to Vm and discharging up to Vm minus Vr, because the charging time is very small and discharging time is very high. So due to that slow discharging, so it can discharge up to Vm minus Vr. It is my ripple voltage. The capacitor charges and discharges once in one time period. If I am concerned it is T naught, then it's nothing but sum of charging time plus discharging time. So we can write T naught equals to T discharge plus T charge. So my time constant RL into C is very large. So that means the discharging time is more compared to the charging time. So I can neglect the charging time. So total time period T naught equals to T discharge. It is my equation number 1. Yes, here I am representing where it is a peak to peak variation in the output. Yes, so here I am calling this VR is peak to peak ripple voltage. Yes, during discharge interval, capacitor loses charge. Yes, so during the discharge interval, the discharge time period, what happens? The capacitor losing the charge. The amount of charge lost by the capacitor during the discharge period can be calculated nothing but Q. Q equals to we know C into V. So in this discharging time period, so some amount of the charge will be lost. So it is I am assuming delta Q. So the delta Q is charge discharges, this delta Q of charge lost in the discharge process. So it can be written as capacitance into delta V. Yes, delta V is nothing but here how much voltage. So it is decreases ripple voltage, that is nothing but Vm to Vm minus Vr. So how much it is decreases? Only Vr. Yes, so it's nothing but decrease in capacity is considered as a Vr. So we are represented the delta V can be represented change. So the peak voltage is Vm and it is decreasing from Vm to Vm minus Vr. So how much it is changes? Just Vr of difference. So we can write delta Q equals to C into Vr. This is equation number 2. During the discharge interval, capacitor supplies charge through the RL. So what happens? So during the discharge, my capacitor is discharging through the load resistor RL. Yes. So charging through the diode, discharging through the load resistor. So amount of charge supplied to load resistor during the discharge period is calculated. Now delta Q equals to amount of rate of charge flow through the load into T discharge. So we know simply Q equals to I into T. Yes, otherwise you can say I equals to Q by T. Yes, I equals to Q by T. Nothing but current is nothing but rate of flow of charge. I equals to Q into T. So here I am writing how much charge discharging through the load resistor from the capacitor delta Q is written as IDC, how much current passing through the resistor into T naught, how much time it takes. It is discharging time. It is T naught. So delta Q equals to IDC into T naught. It is equation number 3. So we know principle of charge conservation. So charge lost by the capacitor is equals to the it is charge supplied to the RL. How much charge entering into the capacitor equals to the how much charge moving out from the capacitor. Yes, so it is can be written as, so delta q both are 2 and 3. We can write C into VR equals to IDC into T naught. From that we can write ripple voltage VR equals to IDC T naught by C. Yes, so we know T naught can be written as F naught, as T naught equals to 1 by F naught. So we can write IDC equals to F naught into C. This is the peak to peak ripple voltage. Yes, now this peak to peak ripple voltage is IDC by F naught into C. Yes, so in this peak to peak voltage VR, so now peak ripple it is equals to peak to peak ripple voltage by 2. We can write it is equals to VR by 2. So ripple waveform is almost identical to triangular waveform. So we can say the output of the filter, the output of the capacitor filter is almost equals to the sawtooth waveform or triangular waveform. So we are considering this one as a triangular waveform to analyze easily. That's why we already know the triangular waveform RMS value is equals to peak ripple voltage by root 3. So in full wave rectifier, bridge rectifier and center rectifier, we shown waveforms. So in that we have written the RMS value of the each waveform. So RMS value of triangular wave can be written as peak ripple voltage by root 3 for triangular wave. So we are considering, so the output of the capacitor filter is almost similar to this triangular waveform. So we are considering that ripple voltage, the ripple voltage RMS value of the ripple voltage is equals to the peak ripple by root 3. So we know peak ripple equals to VR by 2. So it is V dash of RMS equals to VR by 2 into root 3. So we know VR equals to, in previous we derived IDC by F naught into C. From that we can say V dash RMS equals to VDC by 2 root 3 into F naught into C into RL. So IDC equals to, we can write VDC by RL. So from that we can write V dash RMS equals to finally VDC by 2 root 3 F naught C into RL. So now we have to write the ripple factor. Ripple factor is nothing but RMS value. We are getting the ripple factor of output of filter. Yes, we are getting the triangular waveform. For that we calculate the RMS value, it is V dash RMS. So VDC same. So V dash RMS by VDC, it is equals to, so whatever we derived VDC by 2 root 3 F naught CRL by VDC. From that we can write it is equals to 1 by 2 root 3 F naught CRL. So the ripple factor after the capacitor equals to 1 by 2 root 3 F naught into CRL. So this ripple factor R is inversely proportional to the capacitor. and ripple factor R is inversely proportional to the load resistor. Yes. So you can say that capacitor increases, what happens? Ripple factor decreases. That's why we must use the capacitor value must be high. Yes. So when capacitor increases, ripple factor decreases. So the ultimate use of filter is nothing but to eliminate or to reduce the ripple factor in the output of rectifier. So we can use higher capacitors to reduce the ripple factor. Otherwise, you can use higher load voltages. Here, this ripple factor is also inversely proportional to the load resistor RL. So by increasing the load resistor value, we can reduce the ripple factor. Yes. So when you are using the capacitor filter, we can reduce the ripple factor ripple factor by increasing the capacitor or by increasing the load resistor. Clear? So the small ripple factor can be achieved when RL is large or when load current is small. Clear? Any one of that. So we'll discuss about the output current. So here you can observe the waveform in that. So the maximum peak voltage is Vm and it can recharge up to Vm minus R. So the difference is Vr. So it is divided. We have written peak ripple as Vr by 2. So you can say that VDC equals to, yeah, VDC equals to average value. So average value VDC equals to, we can write Vm minus Vr by 2. That's why I'm writing VDC equals to Vm minus Vr by 2. We already know Vr by 2 equals to is equals to IDC by 2 F naught C. So VDC equals to what we can write Vm minus IDC by 2 F naught into C. So that means here we improve the DC voltage and we reduces the or we decreases the ripple factor. Yes. Thank you.